Hi everyone, this is Sri Bhargavi Balja. I'm currently a master student in EC department at University of California, San Diego. Now I'm going to present a talk on interpretable federated learning via neural additive models. Yeah, little bit intro as well as motivation. Machine learning has indeed become a transformative force offering various benefits in the healthcare sector. As the technology is getting processed, various applications are deepening and broadening in the scope, promising significant impacts of the machine learning in the healthcare. Yeah, these are the key areas where AI is becoming strides in the healthcare. First is AI in the drug discovery. Current AI tools have potential to transform AI in drug discovery, thereby enabling research to analyze the lost data sets and visualizing the 3D structure of different molecules in a less amount of time, thereby checking the efficacy of these new molecules in less amount of time. One of the tool is DeepChem, which is a TensorFlow wrapper, which is used to predict the solubility of a new drug molecules as well as their affinity to it binds with the target. And the next key area is biomedical data visualization. One of the tool is AlphaFold 2. It is developed by the DeepMind, which is used to analyze the 3D structure of an different sequences like RNA sequence, DNA sequences. Other areas like improved diagnosis, offering accurate information. So recently developed techniques like in fraud analytics are used to identify the anomaly records, thereby segregating them and building out an model with the remaining records, as well as the disease prediction and the enhanced care. Often these are like black box model. We don't know what is going inside, we don't know what is going inside. So there comes the challenges, like often healthcare providers are as well as the doctors will be has to provide a clear cut explanation of the how the AI system is making the treatment plans to the patients. So there comes the issue like these black box models are making them difficult to trust as well as validate them. So here comes the interpretability as well as explainability and privacy too. So in most cases, the patient's data is transferred between the one hospital to the other hospital later for building up a good model, but that is leading to a violation of privacy. And second thing is insufficient data availability. So these three challenges has provided us an opportunity to explore more in this area. And fourth comes the coronary heart disease. So currently it is observed that there are 12 million deaths because of the cardiovascular diseases, and in the developed countries like United States, uh, it has led to 50% of almost all the deaths. Yeah, a little bit insights about the data set. Cardiovascular study is done on the residence town of Framingham, Massachusetts. It includes 4K records as well as 15 attributes. Here are some vital features: prevalent hypertension, heart rate, glucose level, systolic blood pressure, diastolic blood pressure, as well as total cholesterol level. At the end of the study, we will come to know what are the key features that are highly contributing to it, what are the features that are negatively contributing to the output, and what is the stage at which these features will transfer from the positive correlation to the negative correlation. Like almost all the time, like given a single feature, it won't be always positively correlating with the output. There might be a chance it transfers from positive to correlate to the negative correlation. So that stage we'll get to know from this study. Our ultimate goal is to develop an FedNAM model to predict if a patient has a 10-year risk of future coronary heart disease and identify the most relevant risk factors for this heart disease. We further details comparative analysis of these interpretable FedNAM models with the state of art models. And our ultimate goal is to get the input feature functions of the given output. What is interpretability? It's an ability to explain how a ML model is making the predictions and what are the factors that are driving those predictions. It is crucial for the complex models that are difficult to understand. For example, LLMs, DNNs, these are like black box model. Don't know what is going on inside, but is there giving up and good output. For example, lead poisoning is a leading cause of the development disorders in the children. Some of the factors include paint, water from pipes, ceramics, toys. So using our model, we will be able to know what are the crucial factors among these features. Let's say for genomics too, the features include DNA data as well as phenotypic data. Our model works for the genomics too. So given these graphs, which is plotted between interpretability as well as accuracy. So linear regression has higher interpretability, which means let's say suppose y equal to 4x plus b, x and b are the features. We can easily come to know like b is contributing more to the output rather than x. But that can't be a case in deep neural networks. But we can achieve higher accuracy in the deep neural networks. So we need some model which lies between linear regression as well as deep neural networks that balances the both interpretability as well as accuracy. Some of the latest techniques include RMEC copy, which is specifically designed for the interpreting the radical reactions as well as discover for the computer vision tasks. And here comes the neural additive models. We'll be explaining more about it in the upcoming slides. And there are also traditional techniques like climb and shape, more is sensitive analysis, but there are some issues with it. Shape just provides the contributing score of each feature. It won't provide the graph how it varies with the output. Yeah, here are the neural network models. So in this, every feature is handled by a different neural network. We are concurrently training these different neural networks using a back propagation. Ultimately, will be aggregating the final learned features of the each feature and passing through a sigmoid layer, thereby using it for the output prediction. So we have using these, we have achieved the accuracy almost similar to the deep neural networks, and this can be trained at a massive scale using the GPUs. Also, like these neural additive models are allowing some non-linear flexibilities. Overall, it will be retaining the additive feature at the end. Yeah. We are currently extending the neural additive models to the federated learning context. In the federated learning, we will be collaboratively training the models across the different devices. Using this method, we will be able to achieve the privacy as well as robustness. But there are also other challenges. Like here, instead of sharing the patient's images data from one hospital to other hospital, we'll be sharing the weight parameters to the server. So sharing of an weight parameters from each hospital to the server, and thereby resending back this global parameters to the each hospital, which ultimately lead to a model which is more robust as well as diverse. As I said, there are also challenges like data heterogeneity as well as convergence issues. We will be able to address them by changing of an algorithm at the global model, at the global server stage. Changing from Fed average to Fed scaffold will address the issue of a data heterogeneity. So initially at hospital one, we will be training up a model. Later on, setting up a server, sending the model parameters from each hospital to the server like this, and then reparameterizing the parameters at the server stage and sending reback and sending like global weights reback to the each hospital, and then retraining these NAMs at this each hospital. So using this, we'll be able to get the feature function at each hospital stage. This is basically an architecture of the federated NAMs. Yeah, coming to the implementation, it's an innovative architecture. Like we are extending the neural additive models to the federated learning context. Overall, it led to a network optimization problem. Finally, we have gotten a model that balances the both interpretability as well as accuracy. Finally, we are preserving the interpretability of a neural additive models while leveraging the representational power of neural networks for the higher predictive performance. Ultimately, we'll be achieving the relationship between the each input feature to the output. So we have solved it, as I said, this is a network optimization problem. We have solved it using this optimization at two stages. First stage is at a server's level. For this, we have used a gradient descent algorithm. At the second stage, we will be using normal optimization algorithms for solving this. So finally, we'll be getting this f11 of x1, f21, x1, f31, x1 for the specific feature. Later on, averaging all these feature functions will get an ultimate feature function of x1. Coming to the results, we can many things from these results. Like initially from this age graph, see we can clearly see that with the increase in the age, risk is also getting increased. That coincides with the real world scenario. Whereas for the third graph that is plotted between hypertension to the risk, at up to certain age, this hypertension risk is getting increased with the hypertension. Later on, after certain age, the risk is getting decreased with the hypertension values. So from this, like we can infer many things like what stage this risk is getting from positive to negative stage. Like these values are crucially useful for the hospitals, like for the doctors, as to provide the preventive care for the patients. Yeah, these are all, some of the other results. So we have compared the FedNAM OX scores with the federated DNNs. It is observed that a little bit accuracy got degraded, but that is okay. We have got some good interpretable model. Yeah, there is a little loss in the accuracy of a federated NAMs compared to federated deep neural networks. These are the results plotted for the single hospital. See, from the last graph, we can infer that like with the increase in education level, risk is getting reduced, which means the patient is getting more aware of what factors to choose and how to get elevated to them. But after a certain stage, risk is getting increased, which means that he's spending more time towards education, not giving enough time to the body, or like enough exercises. So yeah, overall summary. Federated NAMs allowed us to train a state-of-art generative models for the deep networks. Ultimately, we have got an accurate, interpretable, as well as flexible model. It is observed that features like resting electrocardiographic results, cholesterol are positively correlated with the output, but whereas features like fasting blood sugar, age are negatively correlated with the results. We have also tried it for a diabetes dataset. It is observed that blood glucose, age are highly correlated. And currently, we're building easy to use tools so that everyone can train the federated NAMs, and also exploring other ways to combine the federated NAMs with the CNNs, ongoing on the future work. Yeah. So currently in the Boolean lab, we are working on the interpretability of a large language models, as well as extending the ID setup to the non-ID setup, and checking these federated NAMs to the diverse data sets other than the diabetes as well as CST data sets. Moreover, doing a mixed patient quantities of a large language models, and doing the image segment of a colon cancer images using YOLO V8. Yeah. If you want to work on it, you can email me, or we can discuss further in the networking lunch. Do you have any questions?